lecture. There's so many things I want to say, so so this is the outline. Okay, so last time I introduced certain notation, so let's review that. So I is a sequence of simple roots. Sometimes it's recorded by integers, I1 to in, and we define the Bottsamelson variety with respect to this I, which is the quotient space by this Bn action. So the goal is to prove this last statement. So the Newton-Okounkov body of Bottsamelson variety is a certain polytope coming from toric degeneration. So let me introduce this toric degeneration of Bottsamelson variety and also toric degeneration of line bundle on Bottsamelson variety. And to talk about the Newton-Okounkov body, we fix a divisible flag. So there is a line bundle Bottsamelson, and then degenerate to a bott tower with a certain line bundle on this bott tower. And if that divisor D defining that a line bundle is a base point free, then the Newton-Okounkov body is actually the Newton polytope of this divisor D. So that's my major claim. But before going to that,
is this bott tower unique? Actually?
Yes. So everything I will introduce you a very special toric degeneration. And I will introduce a special toric degeneration of line bundle and admit. Those are all. So basically, I am constructing one specific Newton-Okounkov body coming from one specific toric degeneration. So yes, not a general statement here. Yes. Before doing it, last time I think I somehow caused confusion by saying lots of stories together about line bundle and divisors. Basically, I think the main reason that you may be confused is that I identified all the line bundles opto-isomorphisms. When I put this equality sign, actually what I meant was the isomorphism. And also the divisors, I also identified all of them up to linear equivalence. So for those who are still uncomfortable with these line bundles and the divisors, I just found a way to introduce this. So so we fix on this normal Noetherian scheme. So we are working with a non-singular variety, so you don't have to worry about it. In this situation, all the set of line bundles, opto-isomorphism, can be identified with these invertible shifts, opto-isomorphisms. So people keep changing this terminology, name line bundle and invertible shift. Actually, that's by this connection. So now, suppose this is what Professor So kept asking. So suppose you have a line bundle with a given non-zero rational section of the line bundle. Then you can assign a certain divisor, namely the divisor of the section.
Effectively that?
No, this is actually a rational section. So effective divisor will, regular section locally defined by regular function. So you will get effective divisor, a rational section. So you may have a pole. So this is just a divisor, which sits inside a Weil divisor, the formal sum of these prime divisors. But this image actually. Huh?
What is y?
This is the set of Weil, yes, Weil divisor. Yeah. Still, I'm not good with the pronunciation. Weil, yeah. But this is isomorphism. The thing is, last time so if you have a divisor which is locally example, you can assign a line bundle, which we use this notation O of D with a rational section which is coming from this constant function on X. This is isomorphism. So now, so our Newton-Okounkov body is in this level. You forget the rational section. So that's is the Picard group. And now, so two rational sections of a given line bundle. So if S and S dash is rational sections of a line bundle, then this S over S dash is actually well-defined rational function on X. So therefore, divisor of S is divisor of S dash plus, so let me use F for this rational function, the divisor of F. So these two divisors are linearly equivalent. So therefore, you get to this. So you mod up by this principal divisor, namely all the divisors, which is the divisor of a one rational function. Here too. So the set of Weyl divisor up to principal divisor is called the class group. Here too is the same. If you have a divisor, you have a line bundle. So you can start with a line bundle and you talk about the Newton-Okounkov body, or you can start with a locally principal divisor and think about the Newton-Okounkov body. So that is one sort of like a dictionary between line bundles and divisors. Okay, let's do the toric degeneration of Bottsamelson variety. So this toric degeneration is actually coming from a certain deformation of Borel group action. So what I mean by this. Okay. So first, fix a one parameter subgroup of this Cartan subgroup. Okay, so you can you can just restrict to this GLN. Then H will be the diagonal matrices. Okay, so what I mean is, so let me introduce notation. So it is a K star to H such that the multiplicative character corresponding to simple root of mu of theta is always positive power of mu. What I'm saying, theta. So for all for all simple roots alpha for some q, which is positive integer. Okay, let me give you just example. So the simplest one, GL2, and we have only one simple root. So let's say mu is K star to diagonal matrix. So theta goes to, say, theta 0, 0, 1. then e to the alpha mu of theta. So here we have only one simple root in GL2, namely using this lattice is 1 minus 1. And this will be theta to the power 1 times 1 to power minus 1. I'm sorry, what am I doing? Yes. Yeah. Well, yeah, I just got confused in multiplication. So what is generally is this, right? So then this will be theta to m times theta to minus n. So it's theta to m minus n. So you just take any m, and since the m is greater than n, so say you just choose anything such that this is positive. Just to fix one parameter subgroup of Cartan group satisfy this. You will see why we just made a choice, and now by using this one parameter subgroup, we have an action of this one-dimensional group, multiplicative group, acting on B by theta x on B, just at the inner automorphism by conjugation. What I mean is that okay, let me introduce an notation. So let me denote this one as mu theta of B. So here mu theta of B is nothing but the conjugation by theta. So it's theta 0, 0, 1. And so B is an upper triangular matrix. So let me denote that one as B11, B12, B22. And inverse of that, if you multiply them, what you get is B11 and theta times B12, 0, B22. So the thing is that you will have theta, but always you have positive power of theta. So what happened is that so you can continue this action to 0. So what I mean is, so this action can be continuously extended to when theta is 0. Just let theta goes to 0. And in this case, you notice that actually, it's nothing but projection of this Borel subgroup to Cartan subgroup when theta is 0. So such that mu 0, so the endomorphism coming from this 0 is actually projection. What I mean by projection, Borel subgroup can be decomposed into H times unipotent subgroup, right? So it's the projection. Okay. Now, so define another algebraic variety as follows.
So what is mu zero? Mu zero is
So
mu zero.
so each
Mu is from
so
mu theta.
mu of theta gives you an element in H. No, what I'm saying is using this one parameter subgroup K star X on B. So each element theta will give you endomorphism of B. So mu zero is the endomorphism of B, but that's And now we define that with the one parameter K. Okay, so alpha I1 cross P alpha IN. Now the Bn acts on this product space but slightly different way. So theta P1 Pn and B1 Bn acts on this on the right. Okay, so theta is fixed P1 B1, but instead you have a B2 inverse P2. So here you have P1 inverse is multiplied to P2 on the left, but here you have this lambda theta of B1 inverse P2 B2. And lambda theta B2 inverse B3 B3. So the Borel subgroup B acts with parameter theta.
What is lambda? Lambda says
Oh, mu. Sorry. I changed lambda to mu because we use lambda so for many things.
so you are twisting lambda 1 by some
Yes.
conjugation.
Yes. Okay. Now, so it has a projection to the first vector. Now, this is a flat family. This is a family such that so I use that. So if theta is non-zero, so let me use so suppose that's I denote that map by pi, the fiber over theta. So now let me just use the notation z theta, okay? It's isomorphic to the Bottsamelson variety. This is just easy to see. And theta is 1, just P1 inverse. Okay? And then pi in. So this is we call a generic fiber. And a special fiber. Okay, from now on I will use this notation is a smooth toric variety. In fact, it is a Bott tower. The proof involves computations with lots of indices. So I'm not going. We just work on this example, this simple example. So let's do it.
Sorry, is it different from Pasqui's?
This is the Pascal. Oh, thank you so much. So this is not done by me. This toric degeneration is actually done by Grossberg and Karlsson in the symplectic geometry setting. But then Pascal put it in algebraic geometry setting. So this representation is from Pascal, but all the computations you may see, the detailed computation you can find in Grossberg and Karlsson.
So the Z theta and BSI are slightly different with this action. B1, you are multiplying this on the second the B1 inverse. Instead of B1 inverse, you are multiplying it by twisting by using or, right?
Right. So
if theta is not 0, then this is so this is nothing but you are twisting this section by torus conjugation, but still it is a Bottsamelson variety.
it is. It's isomorphic to Bottsamelson variety.
The Bottsamelson variety by definition is with this one, this section. It always takes up this section. Right?
Yes. So when
But this is not. This is a slightly different action quotient. So.
so Bottsamelson variety, you can see this one as the fiber over 1.
Z equal theta equal 1, then.
The theta is 1. When theta is 1,
Then. Theta is
mu of 1, it's just nothing but 1. So
But if theta is not 1, then still you have to.
so there is a isomorphism, right? Exactly the isomorphism will be done by this. So, yeah. Okay, so let's see what happens in, so say G is a GL2.
This is the origin degeneration.
Yes, that is the toric degeneration I am using. Well, okay, let me introduce the line bundle as well. So any line bundle.
죄송한데 아마 지난번에 얘기한 것 같은데 바사멜슨과 바타오의 가장 큰 차이가 그러니까 라인 P1 분들인 건 똑같은데 라인 분들 썸으로부터 나온 건지 아니면 그게 가장
그렇죠. 네. What I'm trying to say. So say so any line bundle on Bottsamelson variety can be represented as follows. It's so K cross. Sorry, what I mean is P alpha I1. P alpha I n cross K M1 alpha I1 Mn of in. I'm defining the notation. So this m is a vector notation. Comes with n integers. So please remember omega in's are fundamental roots. So acted by bn.
What is K M1?
Sorry, I'm using this, right? So K is field. When you have a group G and you have a root lambda, K lambda is one-dimensional representation by G dot theta is e to the lambda G times theta. It's the standard notation. Okay.
So that's in n coordinates.
So we have n b's. So n b's acts on this following exactly the same action on Bottsamelson variety, and b1 acts by this
But this
character.
one is actually you are restricting bn to the field to the Cartan subgroup, and then Cartan subgroup is one dimensional.
So every character on Cartan subgroup H can be extended to character on Borel group. So if you have upper triangular matrix, you just look at this diagonal matrix. Yes. So yes, this is a character. Those are characters on H, but we can see that on it. We can extend the characters of B. Yes. Okay. So that is one line bundle on Bottsamelson variety of I. Okay, now we define script L. Just naturally what I just did is I just defined a line bundle on this one parameter family. So just to emphasize that this action, Bn action on this, is different from Pascal, the Bottsamelson. The action of Bottsamelson, let's put a theta, okay? So the Bn action on this one parameter subgroup, one parameter family, is different from the Pascal. So if I put like that, and then this is the line bundle on Bottsamelson variety, and we use this Bn theta action, we can also define the line bundle on script Z. Exact the same. We just use this deformed Borel action. Then, so this is a line bundle on Z. So please, we have this peak. And there is on top of 1 we have Z1.
Is it usual putting En in multiplication is off the part. And you just
Oh, I see.
usually right in the lower.
So for me, one on the down somehow looks like a fibered product, but also I saw this one as well. So please use your own notation. So for this lecture, I decided to put it up.
You know, in usual the transformation group, when we are talking about group actions, sort of a Bible for all these notations is by Breton. And if you
I
look
should
at the
change it.
Breton's book, then usually it's twisted product. Well, some people say balanced product. And then we put it in the...
So this is very this is a very the standard action.
Yeah, I mean, when you're talking about group actions, this is a balanced product.
balanced product.
Or twisted product.
So
in this side you have inverse, and in this side you have twisted.
Well, so in algebraic geometry, we do have this fibered product. So just to distinguish.
But fibered product is over space. This is over the group. So that's a difference, right?
Yes. Yes. Okay. So we have, and then this Z1 is our original object, and let me put this one as a bar tower. Now we have a line bundle over Z, and you restrict on Z1. So let me put that as L1, which is the line bundle restrict to Z1. Then this is isomorphic to LM. Well, that's also straightforward to see. Now, let's see so L0, which is the line bundle L restrict to this bar tower. This is one of our lemma. So this is a line bundle on a toric variety. So any line bundle on toric variety is isomorphic to the line bundle associated to toric invariant divisor. So it's O of D such that D is I will tell you what it is, very explicit described. This one claim. To tell you what this is, I have to tell you what is the fan describing this bar tower. My original intention was to get all of them by one example. Let's see if we can do it. Yeah. So last time we did this simple example, P alpha cross P alpha multiplied by B2. Right? So that is the Bottsamelson with alpha alpha in GL2. And in this case, we somehow know this is isomorphic to P1 cross P1. Again, in this case, this simple case, actually Bottsamelson variety is a bar tower. But now, let's see what is this special fiber. Okay. So what is special fiber? So that one you can understand. So B.
The special fiber is what? A zero case or?
Yes. So that's. Yes, the fiber over zero. All other fibers are isomorphic to Bottsamelson.
The fibers are here. This is a line bundle.
Yes, so to tell you the line bundle, I have to tell you what is the fan constructing.
So your fiber means your fiber means this is bar tower and the bar tower or what?
Yes.
This whole thing is fiber. I don't understand what you mean by fiber, special fiber. So L0 and Z0 and all these are.
Yes. By example, I want to show you what are Z0 and L0 on this example. Okay. So you will see how Bottsamelson is degenerated to a certain bott tower, which is not isomorphic to Bottsamelson, the original one. Okay? So Z naught, you can understand this when it's P alpha cross P alpha multiplied by B2 action, but it has, so let me put this B naught action, that is 0. So how does it act? Say P1, P2 is acted by B1, B2. Say P1, B1. Now this is mu 0, B1 inverse P2, B2. Now again, mu 0 is a projection to Cartan subgroup. So when B1 if B1 you represent this one as a diagonal matrix times unipotent, then this is nothing but T1 inverse. Okay. Now, so there is a projection to the first vector. So this is the projection to the first vector, and that is isomorphic to P1, just to understand. And let me define a line bundle. I'm using this notation. L minus alpha, P alpha. Again, the same way to construct line bundle. K minus alpha, and this is a line bundle on this base, and claim that Z naught is actually this projectivization of this trivial line bundle on the base direct sum with this line bundle. So it is a bott tower. It's not difficult, it's just the computation of this weight.
Why is 0 1 times L?
Are you asking me? Yes. If we have more time later, I will show you the computation. It's just computing the weight of this Cartan subgroup action. Now, okay. Actually, there are lots of, and the key point is that Grossberg and Karlsson actually gave a description of this bott tower as a C2 minus 2n multiplied by C. Oh, all of a sudden I put the C. K. And K star n. So, Grossberg and Karlsson gave very explicit quotient construction of the bott tower. But the writing is very complicating actually. Here, what it means is that here, so we have 2, so C 2 minus 0 square C C star 2, and it's Z1W1, Z2W2 acted by AB, and this A acts on this diagonally. This B acts on this, the second one diagonally. But there's a twisting by A to this vector. So it's A2 not minus alpha, but this alpha with alpha check. So that's the weight. I hope.
So you're saying that I mean, with this explicit construction of this one,
Yes.
you can check that it is actually projective animation of these two line wonders. Or is that what you're saying?
Yeah, so Grossberg-Carlson gave us two different expressions actually. That this quotient construction and this projectivization as well.
Yeah, right.
And from this expression, so this one is actually, you can understand this one as a GIT quotient of K to N. The GIT quotient of certain GIT quotient of K to N, and it's always toric variety. And you can, so from this explicit expression which I'm now writing down, you can construct fan, construct the fan of Z naught. And let me tell you what it is, because I have to tell you what is D. So let's see. So I am just telling you what is the fan. So it depends on the choice of coordinates. So to say E1 plus En plus with the standard basis of Zn, then En minus is by definition minus En plus. The En minus you just negate, but there's a factor which is alpha In minus 1 check, and En plus. And let me just tell you second one. So again, you just negate that there's a modification by alpha In minus 1, alpha In minus 2 check, En minus 1 plus, minus alpha In minus 2 check, En minus 2 plus. You keep going. So any sigma is a cone of, what I'm saying, okay, well, okay, let me write just, let me say S is the set of these E1 plus minus, En plus minus, then sigma is the fan of cones generated by subsets of this S. So you can use all these rays to construct cone, except any subset of this form EI plus EI minus. So you can use any rays, but you cannot include EI plus and EI minus at the same time, which
So
means
any choice of n vectors will give you n
right. And this plus minus should be alternating. So it is obviously smooth fan. So let's do here. What is this? So E1, E2. So we have E1 plus E2, E1 plus, E2 plus, and E2 minus is just E, the negation of E2 plus, and E1 minus is minus E1 plus minus alpha check. We only have alpha in GL2, E2 plus, which is, so this is 2, right? So it's a minus 1, minus 2, minus 1, minus 2. So that is E1 minus. Now you can use two rates to get this cone. This is a Hertzsprung surface.
But E1 plus and E1 plus, these are both E1 plus minus cannot.
So it is a strictly convex. You cannot have a linear subspace. So this toric degeneration for this case is the degeneration of P1 cross P1 to the Hertzsprung surface. Both those are not isomorphic to each other. Yes, I mean, even though I'm not really presenting how we get, it's a matter of computation actually. Now, okay, so what is D? So now I can tell you, right? So what is the toric invariant divisor? Toric invariant divisor is the sum of these D rho, right? For groups. Rho is one race. So D rho is the prime divisor corresponding to this one-dimensional cone. Comes with a multiplicity. So this is a general form of a toric invariant divisor on the toric variety. So in this case, any toric invariant divisor can be written as something times D, E1 plus, something times D, E2 plus something times D, E1 minus, something times D, E2 minus. Okay? So let me tell you what is this D, our D, for this case. Okay. So let's rewrite for our D. So it is. Oops. So E1 plus.
This is a general fact that toric variety. You have toric variety. This divisors are written in terms of one-dimensional rate.
Yes, yes. Well, any. So you look at the toric variety coming from this fan. Then there are 4 prime divisors. Each one corresponds to this ray. Those are torus invariant. So there's a C-star 2 action, and those divisors are invariant. Now, any torus invariant divisor should be the formal sum.
Okay.
Yes, torus invariant.
G invariant.
Yes, yes. So let me tell you what is my D here, okay? So I'm using D. So this D has 0 coefficient for E1 plus to En plus, E1 plus to En plus, and okay, for Den minus, sort of forgot what is this. Comes with alpha In check with please remember it comes with this line bundle description. So, yes, so this is just to write a better way. Let me put this one as lambda 1, this one is lambda n. So that's lambda n. And the second one, we go backward. The coefficient of divisor En minus is alpha In minus 1 check with the lambda n minus 1 plus lambda n. And you keep going.
What is this? So plus side is always 0?
It is, yes. So for my D, so let D as 0 times D E1 plus. So they don't appear if you don't, they don't appear in this divisor D. And plus, so the last one is, what is, okay, so it's, oh, I didn't tell you what is M. We didn't fix the line bundle yet, right? So say let M is M1, M2, then that gives us M1 fundamental weight alpha, M2 fundamental weight alpha. So this will be M1 alpha plus M2 alpha check, which is just M1 plus M2. So M1 plus M2 times the DE1 minus, and the second one will be M2 times DE2 minus. What I'm saying is this all of D is this L0. So this is the degenerated line bundle coming from LM.
So you can write this one more explicitly than that. In this case, using M1 and Mn.
Yeah, the thing is that, yes, we didn't fix what alpha I1 and alpha IN. So it will be, the writing will be really just like this. Yes. Here is just simple, we have only alpha. So in my paper with Megumi, all these definitions and all these D will be explicitly written. The whole point is that we found a torus invariant divisor, very special torus invariant divisor, which describe this degenerated line bundle. So we constructed that with L, whose generic fiber is our original one. And then we got an explicit description of this special fiber. And this special fiber is very nice because it's a toric variety given with a torus invariant divisor.
So this OD, or this L0, so this L0, this line bundle over toric variety.
Yes. That's the claim. So that's the line bundle over the toric variety, and we claim that is equal to the line bundle of this specific explicit D.
So here, this line bundle, you have a Bottsamelson variety, and then you constructed a specific line bundle Ln, and then after you do the toric degeneration, and then this line bundle changes to L0, which has the divisor explicitly.
Yes. So just want to make it clear, this toric degeneration of Z, the description of Z naught is given by Grossberg and Karlsson and Pasquier. What we did is we found explicit description of this degenerated line bundle. But well, maybe because I found it, but description of D is also very easy to see from Grossberg Karlsson's expression as a quotient space. It's, if you just see how, if you know how to see it, it's just there. Okay. By the way, so what we have. So we start with the Bottsamelson with the line bundle. Our goal is to find the Newton-Okounkov body of that collection, Bottsamelson variety and the line bundle. And now because we have a nice one, toric variety and this line bundle on the toric variety, and
so with that line bundle on this toric variety, you construct graduations.
yes. So
And then the body of this one is nothing but
with one assumption: if the D is a base point free. Yes, if the line bundle on this toric variety is generated by globally generated by sections. So I'm not sure if that assumption is the best assumption yet. So far we could prove this final statement under that assumption. Yes, so I sort of forgot about the admissible flag. Yes, we have to give admissible flag, but also, so here I will give you the flag of subvarieties of this big space, namely. So we need a notation. So xi is a subvariety of script z, defined by that the ith coordinate is actually in B. I'm just putting the coordinate system here. Okay. Then, so this flag of subvariety is sort of starting from Z, and you have x1 intersecting with x2 and keep going. Okay. Now, so you have this flag of subvarieties in Z, and if you restrict that flag of subvarieties on Z1, you will get a flag of subvarieties on Bottsamelson variety, and if you restrict that one into Z0, you will get the flag of subvarieties of Bott tower. So I am using those flags when I'm saying this Newton-Okounkov body. And actually, I'm using Bottsamelson variety has a very, very nice property in terms of this coordinate system. So let's just, okay, this is the abuse of the notation. We intersect this one with the Z0, which is Bott tower. Then you will have, okay, so let me use just, okay, well, whichever, here, let's say, okay, let me use that one as tilde. then this A. The thing is that when you restrict this one, the one important fact should notice is that the xi tilde intersected with y, z naught is actually this prime divisor corresponding to ei plus. So we go back to this picture. So this is the bott tower Z naught. We're looking at Z naught here. Yes. So it has one affine cone, affine subspace here. Okay, so we have cone generated by E1 plus E2 plus. That gives us one affine open set in bott tower. And these DE1 plus DE2 plus are coordinate hyperplane in this Cn. Now, our divisor D does not have the term involving E1 plus E2 plus. It means this divisor inside of this toric variety is disjoint from this C2. So we have this C2 looking at this one specific affine open subset of bott tower. Then this divisor is on the boundary because this one does not touch with C2. So in this LM paper, chapter 6 about toric variety, in that case, so if your divisor D does not intersect with this Cn, then using that coordinate system as to find this admissible flag, the Newton-Okounkov body for this toric variety with this line bundle with this is actually the same as the Newton polyton.
Sorry, what are xi's in the second line, a third line?
Oh, so x1 is the x tilde 1 intersecting with the y. Yes, thank you. Yes, it's better to imagine. What I really meant is that you have family of these varieties, and inside you have this flag of subvarieties, big space, and intersect with the special fiber or intersect with this generic fiber. And so this is the flag by intersecting with the special fiber. Okay. And what I'm saying, that is actually just a coordinate system of bott tower, specific coordinate system in the local coordinate system of bott tower.
Is it hard to see they are admissible flags?
So here, everything is non-singular. Yes, and those are all these subvarieties are smooth. Okay. Okay.
Divisible just means they are co-dimension one decreasing and then each one irreducible. Each yi is irreducible. That's admissible, right?
And also non-singular at the last point. But what I'm saying is, for our case, that is just true because all these subvarieties are non-singular. Those are just
They are the fixed points at certain scores, right?
yes. It's just in C2. It's just coordinate hyperplane x1 equals 0, y equals 0.
But that does not. Oh, that's x1, x2. Okay. Not p. Okay.
Yes, so yes,
So that's,
a lot of, because we are using a lot of geometric objects, the notations are confusing. So, okay. the reason I'm emphasizing that the significance of our paper is by finding this very special representative of this line bundle. You know, you can choose another formal sum expression of the line bundles, right? I mean, up to isomorphism. However, our expression, so D is disjoint. D does not have the term involving DE1 plus DE2 plus. So this choice somehow match, this one match, this D matches with this choice of flag. So again, the Newton-Okounkov body is very subtle depending on the choice of flags. So we got a nice combination. Flag of admissible flag and this line bundle. So this is one fact you can deduce from this general statement in an Lazarsfeld and Mustata. So therefore, it's enough to show that the Newton-Okounkov body of our Bottsamelson Z1 with our line bundle. Okay, if you want to emphasize Bottsamelson, this is our original one and this is our LM. With respect to this flag, admissible flag, is actually equal to the Newton-Okounkov body of this toric variety. It's a very natural expectation because these two objects are sit inside of this one parameter family. And however, it's not always true. If D is base point free, we succeeded to prove it. Okay. I mean, this is a very natural question. Suppose you degenerate your object to a certain nice one, toric variety. Can we say the Newton-Okounkov body of our original one is the same as this Newton-Okounkov body of nice one? And first thing you have to consider is actually what is Newton-Okounkov body construction involves this space. So the Newton-Okounkov body of Z0 involves this space. Newton-Okounkov body of Bottsamelson involves this space. Yeah. We have to find the value. So here is the Bottsamelson. Here's the Bott tower, and Bott tower. We already know this the semigroup coming from this one is known. And we want to show the semigroup coming from this one is equal to this semigroup. So starting from the starting, we have to see if they are closely related. So the first thing we have to see, do they have the same dimension? What about dimension? But to have this equality, they must have the same dimension, right? So to construct the Newton-Okounkov body, we have to compare all the values, and this dimension tells you how many values you will get. And if this one does not match with this one from the very beginning, they cannot be equal. And from this very general fact, which is called semi-continuity theorem, you can find in Harshon chapter 3, 12. It says, in general situation, you have this one. You have flat family. Then the dimension for the generic fiber is at most the dimension of this for the special fiber. And now, so we need to show if these base point free, actually we have to show, so let me use this one as okay, so let me just use H naught of L1 is equal to H naught is 0 of L0. I am now simplifying all the notation, okay? So this is the dimension for that. This is the dimension for that. So that's the fourth thing we have to do to show. The reason I really want to show you this is a wonderful combination of toric geometry and this representation theory. So, okay. So how to show this? Okay. We are dealing with this the simplest question to complete this one. The left hand side and right hand side is just natural numbers. And the right hand side is from this toric geometry. This is nothing but the lattice, the number of lattice points of this Newton polytope. Right? General fact, the dimension of this OD is the same as the number of lattice points of the polytope. So that's one of the significance of this polytope, right? All the lattice points of this Newton polytope gives you its basis. Now the left-hand side. The left-hand side is from Luxim by Littleman, Magyar, the standard monomial theory for Bottsamelson variety. They show that this is equal to number of this is actually generalized. It's not the classical Young tableau. This is the number of generalized standard tableau with shape M. I just want to introduce there's a certain connection. So what we did is that we constructed a bijection from PDZN to the set of the generalized standard tableau. If, again, don't forget, if D is base point free, so by the bijection, and we can get this equality. So for Bottsamelson variety case, if this special line bundle is base point free, actually it's not a semi-continuity, it's constant. The dimension is constant. So that's one strong property, and using a very special geometric property of Bottsamelson variety, we could show that all the values appearing for the semigroup for L naught actually appear as valuation for Z1. But this one, the values for Z1 cannot have more points than that one. So by doing that, in conclusion, we could prove that the semigroup we are constructing for Z1 is actually the same as the semigroup for Z0. So they have the same Newton-Okounkov body.
So you are actually proving more stronger. You have a same semigroup. Because
yes, actually.
Newton-Okounkov body, even though semigroups are different, they can have same.
Yes, so it's stronger, right? We just began with this question: can find an example of a Newton-Okounkov body? So the answer to that one is 1. But yes, we actually found a much stronger one.
So this is a case when you have a line bundle constructed specifically with this representation times this twisted.
Yes.
But you don't know. I mean, there may be different ways. What are the? I mean, you have. This line bundle does not have to have a group action, right? When you do the construction, I mean
LM?
You just need the complex line bundle.
I did not use any group action, but according to Megumi, the reason we are interested in this line bundle is because they have Borel action. Yeah, so it has lots of group actions. So that's the reason we are interested in this object. Of LM.
The first chunkless of this LM is not.
So I am not an expert in that question, but I can tell you. So Grossberg and Karlsruhe's computation to find this C2R GIT quotient, they do lots of these Chern number calculations. But
What is the second homology class of
so
this space? Yeah. Z or Z1.
Oh, you're asking me the Picard group of Bottsamelson variety. It's a free. It's a Z to the. It's the free abelian group of rank 2n. Yes. So yes. That's also I used. Any line bundle can be represented by this M1 to Mn.
So you are any line bundle?
Yes, I said rank 2n. I'm sorry, rank n. Yes.
So you are actually using all line bundles?
So any line bundles whose degenerated line bundle is base point free. So that is hidden here. So you start from LM, yeah, and then you go to O of D. Actually, so this is collection of number, and also that one comes with a collection of numbers which you compute from this one. Yes, actually, checking this one is so easy actually coming from this. So if you give me M1 to Mn,
any M1 to
Mn, I can tell you if that one is valid.
Which one is?
If you give me M, I can tell you the deduced D. Yeah, base point. So base point freeness of D. Yes. So. Yes.
But this M1 to Mn may be corresponding to the first chunkless of this line bundle, because you said that.
구체적으로 계산을 했어.
So you are actually candidate of all line bundles over this, and then the question is whether they are producing this free one.
Right. Yes. So I think the one necessary condition for this is they must be at least non-negative. Non-negative. So one thing if you want, Lm is base point free if all mi's are non-negative, and Lm is ample if all mi's are strictly positive. So that's one known fact in the line bundles. If and only if, actually, yes.
But we are interested in D.
What I'm saying is you're right. I'm giving you like somehow weaker restriction to satisfy this.
Sorry, what I'm saying is M we are interested in when D is base point free.
Right.
But you are said.
Oh no, I'm just giving you one information. If you are interested in when Ln is base point free or ample needs, this is one criteria.
Not D.
No D. So also this PD is very connected with this twisted cube. Twisted cube introduced by Grossberg and Karshun. And another paper I wrote with Megumi is that this twisted cube is actually equal to PD if and only if D is base point free. So I found that there is one interesting question that when is this twisted cube is real polytope? So this is not it's a virtual polytope, and
when that is a cube. Actually.
Yes, the cube. So yeah, so when I say polytope, it should be closed as well. So convexity and being polytope is slightly different, right? So you may have twisted cube, which is convex, but not a polytope. So to be a polytope, it should be closed and convex, and so our answer is actually weaker. We say this is really a real polytope if and only if D is base point free, and of course when is it still convex? And we found one partial answer to that using some positivity of these numbers. So it sort of goes many directions actually.
You are talking non-twistedness, right?
Yeah.
But if the twisted cube is non-twisted, then it is compact, isn't it?
So actually Megumi and me and Eunjung, we found we have to be careful about this untwistedness definition of this and the convexity. We were very confused with these two notions. We actually at the beginning we just sort of identify them, but they are not equal. So by definition, we define. If you don't like it, and just suggest as a better word. So this is really means this twisted cube is a real polytope. Is a polytope.
Convex or not?
Yes,
polytope is convex.
Yes, closed and convex. This is closed and convex. So there are like seven criteria actually.
That is actually combinatorially equivalent to cube, right? Because you are working on hot towers.
Yes.
So it's actually cube.
So it is cube. Yes, it is. So what we proved is that there are lots of equivalence criteria for being for twisted cube to be untwisted. One of them is D is base point free, and actually in that case, this twisted cube is actually equal to PD. So it's closed and convex. But then you can say, well, what about just convexity? Even if it is not closed can we still have convexity? And we have some criteria for that one.
Convexity is slightly weaker than twistedness.
It's weak, right? Yes, right, yes. So for those who are not really interested in polytope, or if you are not so interested in the algebraic geometry, you may not need a really polytope. When you want to talk about toric geometry, you need a polytope. But if you want some pure combinatorial formula for representation, convexity is still nice. So that's what we did. I just want to advertise Eunjung's work too. So we found this. But Eunjung really want to have a strong connection to flag variety. So can we still have some nice one when this line bundle is coming from? If this is a pullback of a line bundle on flag variety, can we still? So if you don't mind, I can say something more. Okay? So. I'm sure Eunjung will present later. So, we have this Bottsamelson variety. So we have this product map to flag variety.
Yeah.
And if this one is a reduced word decomposition, this is birational. So now you have a line bundle here, given by a weight. Then you can have pull back. And this one will be one of them. And then you will have a PD of lambda. And I tried to find out a equivalent, if and only if condition on lambda such that this is a base point free. But I found like two necessary conditions. One of them is lambda should be always dominant. But if I understood correctly, Eunjung and Megumi found a criteria on this I, word decomposition. So if this word decomposition satisfies some combinatorial property, you will have this one base point free, if and only if. So and then that if and only if condition somehow includes my two necessary conditions. That one I have to see more carefully. Maybe they overlap, but not really. Right?